Okay, good evening. It's 7 o'clock. We are broadcasting this lecture live on the dark web tonight, so it had to be done at exactly 7 o'clock. I'd like to welcome you all to the 53rd Annual Jansky Lecture. This distinguished lecture series was established by the trustees of Associated Universities, Inc. and the scientific staff of the National Radio Astronomy Observatory to recognise outstanding contributions to the advancement of radio astronomy. The lecture series is named after Carl Jansky, who was an early pioneer of radio astronomy, the first person to really understand the significance of radio emission from space. He founded the field of radio astronomy and opened a new window on our universe. Now, as we have in past lectures, we're very pleased to welcome the family of Carl Jansky. There's David Jansky. David, stand up. There we go. Thank you. And we actually have some other members of Carl's family here tonight with us as well. It's always a pleasure. So tonight's lecture is The Radio Harvest: Pulsars, Cosmology, Massive Black Holes and Fast Radio Bursts by Professor Roger Blandford. Roger began his career in England studying at Cambridge University and received his doctorate in 1974 in theoretical astrophysics. After a postdoctoral position, he became an assistant professor at Caltech in 1976 and eventually held the title of full professor between 1979 and 2004. In 2003, he left Caltech and became the director of the Kavli Institute for Particle Astrophysics and Cosmology and held that role for about a decade, 2003 through 13. Today, he is the Luke Blossom Professor in the School of Humanities and Science at Stanford University. He is also a professor of the Stanford Linear Accelerator Center. Along the way, he has received essentially every award and lectureship the field of astronomy has to offer. There were 44 lines there, and I won't read them all out to you tonight. I noticed the last one on there was being the Jansky Lecturer. He has held visiting positions at more than a dozen astronomy and physics institutions worldwide. He's received the Danny Heinemann Prize of the American Institute of Physics and the American Astronomical Society, and the Gold Medal of the Royal Astronomical Society. He is a Fellow of that Society and of the Royal Society, a member of the US National Academy of Sciences, and a Fellow of the American Academy of Arts and Sciences. His research interests cover many areas in radio astronomy, including quasars, pulsars, and supernova remnants, as well as cosmology, using gravitational lensing and the cosmic microwave background. Roger's work in explaining the formation and properties of radio jets form the basis of our understanding of this important phenomenon seen on many scales throughout the universe. So we're delighted to have a scientist of Roger's stature here for the 53rd Jansky Fellow, so please join me in welcoming him. Come on, Jeff.
Well, thank you very much.
Thank you.
Bring the slides up. Do you have to? Oh, there we go. There we go, thank you. Well, thank you very much, Tony, for your very kind introduction. It is truly a great honor for me to be here and be the Jansky Lecturer, and also an honor to meet David Jansky and other members of the Jansky family. And it was very nice last night to learn much more about Carl, who really is, as Tony said, the founder of this field. Here's picture. Oops. Not quite on yet. There we go. There we go. So there's Carl Jansky. If you'd like to see a picture of him in front of his famous radio telescope. And he was in the 1930s was sent by Bell Labs essentially to investigate radio interference and so on, and he discovered thunderstorms, but then he discovered something much more important, which was a signal that was coming from outer space, and he could tell that it was actually coming from somewhere outside the solar system, and he identified that correctly with the center of our galaxy. What I'd like to do here is is talk a little bit about where this field has gone. I'm going to talk not just about Carl Jansky, but other pioneers of this field. I'll say just a little bit about essentially 4 or 5 streams and of scientific research, and try and give you a little bit of idea where things started and why they started, and then where we are today, and perhaps track forward a little bit from there. And I've called these harvests, and the ones that I've chosen to emphasize here are basically radio telescopes, what we call radio galaxies, cosmology, the search for extraterrestrial intelligence, and then pulsars. Now, there's much more into radio astronomy than those topics, but they're ones that I personally have been interested in over the years. And so I'll say a little bit, as I say, about, if you like, the harvests that have been grown out of these initial seeds, but also some of the things that I've been interested in recently. And I'm going to put my neck out and try and project forward as to where these fields might be going in the next few years. So there we go. So there's a reconstruction of the telescope that Jansky used, and he, as I say, he started this field. The next person really and that's, of course, I should have shown that here. That's the Jansky Very Large Array in New Mexico, and so that's the telescope that's named after Carl Jansky. So here's another early pioneer who I had the privilege to meet many years ago, Grote Reber, and his telescope. He's just there in Illinois, and he was a real genuine amateur astronomer, and he did a formidable thing. He built enormous radio telescopes, and I've just been privileged to see some of the archive of all the work that he did, and he discovered genuine radio sources out there in the cosmos. That was truly remarkable. He discovered the famous sources we're going to come to. Cygnus A is one of those we're going to talk about a little bit. And this was known, both the work of Jansky and of Reber were known, and then the Second World War happened, and people were working on radar, and not surprisingly, they developed the mechanical and in particular electronic capabilities to advance the field, and very quickly there were other telescopes that were built. Here's one in Manchester in England, another one in Cambridge in England. I grew up with these. Australia there, where Tony grew up. Here's one a bit surprising. This is Palomar Observatory, and that's a 200-inch telescope, not the place you'd find a radio telescope, but this is where the early Caltech telescope was actually constructed, and then it was moved to another observatory in the Owens Valley. And then finally there's one in the Holland. And this was just a representative set of telescopes. So very quickly in the 50s and the 60s, radio astronomy grew. And the thing you should notice about this, I'm not going to tell you what they did or how they behaved or so on, but they were all different. And so people were experimenting like crazy. And what you got is a crew of the early radio astronomers, some of whom are here, who were sort of famous for their technical ingenuity, but also their scientific curiosity. And it was that combination of expertise and just being inquisitive, nosy about the universe. It was that combination that led to all the great advances which are continuing to this day. And I hope that this talk will make you think that this isn't some played out field or something. The rate of discovery has not let up. So this is a slide I like to show just to give some sort of physics context to astronomy in general, but also radio astronomy. What we see here is what we astronomers call the electromagnetic spectrum. So we're used to, most of you are used to a spectrum, you might see as a visual light. And for visual light, that really corresponds to just 1 octave. Now, is 1 octave of what, you might say? Well, there's 2 things that you use to characterize waves that you see in the electromagnetic spectrum. One of them is the frequency, and the other is the wavelength. And so visual light, what you can see with your eyes, has a range of frequencies, and equivalently, just the same, a range of wavelengths. And that's just a factor of 2. In sort of round numbers, it's 400 nanometers, we'd say, to 800 nanometers. So that's the range of wavelengths that you've got. Now, if you look at the whole electromagnetic spectrum, almost all of which is accessible to astronomers, then it ranges all the way here from the lowest radio frequencies to the highest energy gamma rays, right up there. And when we're down in the radio range, we talk about them as waves and so on, a bit like waves on the ocean. And when they're up in the gamma rays, then we think about them more as particles, as photons, and so on. And so there's this huge range here, 70 octaves worth, 10 grand pianos worth, if you think about it as a sort of a metaphor using sound. But in addition, we have now gravitational radiation observed directly, as everyone here will know, and there's a spectrum there. Not all of that is accessible as yet, but one day it will be. There are cosmic rays. These are energetic particles that go with energies as high as the highest energy cosmic rays have energies comparable to that of a well-hit baseball. Think about that. And that's another window on the universe. And then neutrinos. They have just been associated with the radio source. So we've got essentially 140 octaves worth of spectrum there to explore. So there's a lot for astronomers to do. And as you keep on opening these up, the spectral bands up, then you get more and more information about the universe, and you piece together all the big puzzles about what's going on out there. So 140 octaves to explore, and a lot of it, sorry, I should just mention that point, a lot of it is associated with these 3 grand pianos worth, more or less, is associated with radio astronomy. Okay, so radio astronomy today, let me just show you telescopes. I'm not going to comment on them, just as I'm sure many people here are quite familiar with them. Here's the Jansky VLA, here's the Grain Bank Telescope, here's ALMA in Chile, which was a joint venture between the United States, the Europeans and the Japanese, and also, of course, the Chileans, and that's a millimeter telescope. So this is one that is for radio astronomers, very high frequency, very short wavelengths. It's called a millimeter telescope and a sub-millimeter telescope, and that's the one out in Chile. This does lower frequencies out at Green Bank. This does sort of in between, if you like. And then here's another one. This is the VLBA. This is it's actually not one telescope, but it's 10 that's used in combinations with more. And here the point is to use the telescopes in different places, in this case more or less in the United States, different parts of the United States, and you use this combination to get very fine resolution. The further apart the telescopes are, the better the resolution, the finer detail that you can see in these sources. And this is one that's used very successfully in the United States. This is actually one in California, this particular dish, but I say there's 10 of them, and this is called the Very Long Baseline Array. So it's also very much a global enterprise, radio astronomy. There are big telescopes all around the world, and they're being built. Here's a new one, 500 meters. It's fast. It's in China. It's as you can see, it's constructed. There's work to do on doing the receivers and so on for it, but this looks like being a very exciting telescope. Here's another one. This is one in South Africa called Meerkat, and this is and then there's another one. This is the Event Horizon Telescope. This is a combination of telescopes that essentially does the same sort of thing as the VLBA, gets very high resolution. I'll come back to this at the end, but this one works at millimeter wavelengths, not so much centimeter wavelengths, and therefore sees correspondingly finer structure still. And we'll talk about that a little bit further on. And then finally, two more, sorry. Here's Radio Astron. This is again doing this very long baseline interferometry. It's a Russian satellite, and it's the one that's working now, and it's working out in space. We'll see some examples of that. And so if you go out into space, you get even further separations between the telescopes and even better angular resolution than putting them on the ground. And then finally, there's something I will talk about a little bit in the cosmology. This is a satellite in space that observes the cosmic microwave background. It's called the Planck satellite. This one is one led by Europe, but there's a lot of American participation, and we'll see some results from that. So this is very much a sort of global enterprise. And if we look to the future, as I say, I'm going to go through each of these, if you like, growing seasons, if you like, and so the future is the, firstly, there's the NGVLA. This is the future of, from the United States, the program looking forward to the future. If we look at the square kilometer array, this is an international version. This is going to be a much larger type of multiple telescope called an interferometer. And what I showed here was the precursor to this. This is a South African telescope called Meerkat. And this South African telescope is not just pictures on a proposal. This is a working precursor, and it's been exciting radio astronomers by how well it is working so quickly. And this is a picture of the center of our galaxy. And I'd like to show this one because this is what Carl Jansky, of course, looked at. I just can't imagine what Carl Jansky would have made of this. This is the center of our galaxy, which he discovered at 2 degrees or so across. And what you can see here is a new discovery. We've never seen anything quite like this before. These filaments here like this, which many of us suspect are magnetic fields and so on. So this is a remarkable image made by a new telescope. Going forward, a lot of the future is likely to be also at the very longest wavelengths, lowest frequencies, longest wavelengths. There's a lot more to be explored there, and that's going to be one of the frontiers. And for the final, I think what I think is going to be, again, a frontier, and it's one that is not very much discussed at the moment, but I think it's going to make a resurgence, and that is using telescopes in space to do very long baseline interferometry to get these very fine detail inside the sources, and that this is actually a Chinese project. I don't think it has any real developmental status at the moment, but I think there will be many more investigations in the years ahead of orbiting VLBI, having much bigger telescopes out in space, making, as I say, these very fine images of distant radio sources. So I see this very much as being in our future. So I'd now like to transition from this business of telescopes. I'm not really competent to discuss this. I'm what's called a theoretical astronomer, so I've never built anything that worked. I've broken a few things, but I've never built anything that worked. So I'm in awe of all that has gone in to make this here. And as I say, every time I come to NRAO, I just take my hat off to the people who make all these wonderful telescopes work. So let's talk about now the radio galaxy harvest. And this is just, I'm going to talk about how we went from there, if you like, to there. So, so what I was going to do was take you through a little bit of a sort of starting with a history, and then where we started collectively as astronomers, and then where we ended up. So, if you like, the first as you know, there are a lot of galaxies out there, and these galaxies have nuclei, a bit like atoms have nuclei. So galaxies have nuclei, and the first evidence that there was something going on in the middle of distant galaxies, before actually people quite knew what they were, was in 1908. I'm actually showing here a slightly different galaxy than the one that was studied then, but it's one essentially in the same class. It's called a Cepheid galaxy in 1943. Again, it was seen that there was a lot of activity going on right in the center of this particular galaxy. If we look at Virgo A, I've given them names that are more memorable for you, but maybe not the familiar ones for the astronomers. So I call this one Virgo A, and this is a galaxy in a cluster of galaxies. It was actually first studied in 1918 at the Lick Observatory in California, and this was the first known example of what Tony referred to, which is a jet. This is a linear feature, if you like, seen in this case optically, coming out of this nearby elliptical galaxy. Another source that was actually discovered by Groth-Reber, because it passes overhead in Illinois, where he had his home, is called Cygnus A. And in 1953, a remarkable discovery was made by Jenis and Dasgupta, and they showed that the actual radio source was not an image that was centered on the actual galaxy. It was two images straddling the galaxy, one on either side of the galaxy. This is a remarkable discovery, and one of many. And then the final example I want to use is something, I can't call it something A, but it's called 3C273, and this is the first quasar that was discovered in 1963. And again, radio astronomers had a large role in this. My once-time colleague, Cyril Hazard, found these radio sources were known, but people didn't have very accurate positions for them, and he had the clever idea of using the moon, and as the moon passed it, it vanished, and then it came up again when the moon passed it by. And so you got essentially two coordinates on the sky, and you were able to get a position of this source, and that position was good enough to find the identification of the galaxy. And another former colleague of mine, Martin Schmidt, was able to take an optical picture of what was at that position, and was astonished to realize that it was very distant, and therefore it was very, very luminous. You see something, certain brightness on the sky, and it's very distant. That means it's extremely luminous. And this was, who already knew, outshone 100 normal galaxies. And we now know quasars that are even brighter than that. And before very long, it became very clear that the center of this object was active and variable and very, very compact, very small, very, very compact. And so we had an even more remarkable example of this sort of active galactic nucleus, and it now turns out that we know that every normal galaxy has a tiny nucleus in it, and that may well outshine it. And on the basis of evidence that I won't go through completely here, we now associate that nucleus with a massive spinning black hole. There's a black hole there that's a massive, millions to billions times the mass of the sun. It's spinning, and that is ultimately the source of the activity that's responsible for the optical activity you see there, the jet you see there, these two giant lobes, or giant lobes of emission you see here, and then the jet that you see here, which you can see, this was in the first papers that were written. This was, you see an optical jet there, which Martin Schmidt showed, and then you saw what Cyril Hazard saw, which was essentially a radio feature that was elongated in the same direction. So I'm just going to go through these four sources because they all have something to tell us about this subject. Okay, so before I do that, I ought to just say a little bit about black holes. This isn't a lecture on general relativity, so be relieved, but it is. I just want you to get the idea that relativity is an extension and a foundation of the Newtonian theory of gravity, and it basically says that space-time is curved, and when it is extremely curved, as shown schematically here, then that means you've got very strong gravity, you've got a black hole formed, and we know, according to general relativity, how to describe that, and it turns out really all you need are two parameters to explain it, a mass and a spin. Now, the first person to use, well, he actually wasn't the first person to use the phrase black hole. It had an Australian journalist was the first person, but the person who popularized it was John Wheeler, an American physicist, and he realized the importance and the challenge to physics that was raised by black holes, and he got a team of students and so on who worked out a lot about them. Here's another person, Roy Kerr, and what he was able to do was to do the mathematics. He's a New Zealander, and he was able to do the mathematics that described the spinning black hole for the first time. It was a kind of a miraculous piece of mathematics, but it works. And then here's Roger Penrose, who was one of the many people at that time who figured out some of the most important properties of these black holes according to general relativity. And then finally, Stephen Hawking, who, again, somewhat in collaboration with Roger Penrose, but also independently, was able to define the mathematical and physical properties of black holes according to general relativity. And these remarkable accomplishments made in a very short space of time in the late 60s and early 70s. So that's black holes. And as I say, the astrophysical ones are just described by two numbers. They are very, very simple. And it's just mass and spin that you need. Okay, so I want to say a little bit about energy and extracting energy from black holes. firstly, just thinking a little bit about energy. This is a gentleman of Greek extraction. His name, or actually he wasn't quite, but his name was, it's a Greek myth, but not a Greek extraction, but he's Sisyphus. Does anybody actually relate to his daily... Okay, yeah, so he rolls the ball up the hill and then it comes down again. So let's suppose he rolls this 10-ton boulder up a 100-meter hill and then he watches it roll down every day. It was a punishment. Okay, so he does this and there's a certain amount of energy released. Now let's think about how much mass we have to use to release the same amount of energy by a different means. So you might think about explosions. So you go to, say, 3 kilograms of TNT would release the same amount of energy. So that's quite a lot. Okay, now, actually you do better by using alcohol, generally speaking, and candy and so on. So that releases even more energy in round numbers. If you go to nuclear power in a nuclear reactor, we're going micrograms. Micrograms is not a kilogram, which is 1,000 grams. It's a millionth of a gram. So 100 micrograms of uranium will release the same amount of energy. But if we put energy around a black hole and release the energy, just like Sisyphus rolling the ball down the hill, then you only need 300 nanograms. So that's a billionth of a gram, or a trillionth of a kilogram, and almost anything there, it's indiscriminate. It can convert that energy to energy. So we don't need very much mass in the vicinity of a black hole to release the energy. But there are actually two ways of releasing the energy, and I'll come to this in a moment. One of them is directly from doing the Sisyphus thing and taking some mass and then reducing its distance from the black hole and releasing energy in that way, just going down the gravitational field, if you like. And then the other way is if the black hole is spinning, just like a spinning ball or something like that, there is a certain amount of energy associated with that, as much as 30% of the mass of the mass energy of the black hole. That energy is also releasable, and it's that many of us believe is responsible for making the jets. So, there we go. So let's go back to our four sources. Here's Perseus A, and that's the image I showed you. This is what radio astronomers have made of the radio source that looks like from it. So this is a radio jet, now seen with VLBI. This actually uses radioastron, and there's a black hole in the middle there. And what they have discovered, as has been seen in other observations, is the jet that comes out of this is you're seeing the emission not from the center of it, but from the walls. It's the interaction probably with the surroundings that is actually giving you the emission. This is a very recent discovery. This has only happened over the last year, this image. If we look at it in more detail, at the center, the black hole is there. We can see this emission, as I say, from essentially the walls of this funnel. So we're starting to see the sort of internal plumbing, if you like, of these jets. So this is all very recent. So this is as it's Halloween, I thought I'd better show you what happens to these jets. This is an X-ray image of the cluster of galaxies around it, and what these jets actually do is make giant bubbles. They blow bubbles in the surrounding gas, and you can see them here. It isn't a Halloween mask, it's actually an X-ray image, and you see those bubbles. And the gas, this very hot X-ray emitting gas around here, is heated by the black hole at the very center of the associated galaxy. It's kind of extraordinary. So this is seen, and then, so what we know just from the ability of these telescopes to resolve structure close to the black holes, you got into about 300 times the size of the black hole. That's the sort of resolution you have. That's the sort of structure you're seeing. If we move on now to Virgo A, this is the galaxy, and there's bits of the jet there. Then here's the cluster of galaxies around it. Here's a low-frequency image made with a Dutch radio telescope, and we see the jets off in opposite direction. And again, they're blowing these bubbles and heating the gas around them. So you can see that. Now if we look on the finer scale, if we use X-ray telescopes, we can see the jet right in the center. If we use a radio telescope, this is made by Craig Walker and his colleagues here. This, again, you can see this sort of emission from the walls of the jet, and the black hole is in there, and you only see the jet on one side. And then if we look here with the finest resolution to date, you're starting to look on the scales now of around, it depends quite how you measure this, but I would say 10 or so times the size, 10 or maybe 30 times the size of the black hole. You're sort of homing in. It's like a sort of microscope. You're looking with better and better resolution. And you can see this structure again. So you can see that it looks like the emission is coming from very close to the black hole at least, and I would argue probably it's the spin of the black hole that is responsible for making this jet in Virgo A. The black hole there is 6 billion solar masses. That's the mass of it. It's one of the heavier ones we know, and that's pretty impressive. So it's not surprising there's a lot of energy associated with it. Okay, Cygnus A now. As I say, this is what we started off with in 1953, was lobes on two sides. Now, let's look at it again. The pink stuff here, or the red stuff here, is the radio image. That's the radio image. There's a galaxy there. There's some optical here in white. There's a galaxy in the middle, and in the middle of that is a black hole, about 1 billion solar masses. There are jets you can see coming all the way outside the galaxy and fueling on either side, fueling these two giant lobes of radio emission. It's pink and so on. The blue stuff is X-rays. So you can see the X-rays, and the X-rays are all part of the story of what's going on here. So what we have is in the center of this galaxy is a spinning black hole, and it creates these jets, which we see going out, inflating these two lobes on either side here, which Jensen does up to that, but we can see all the fine detail now. This is what it looks like in the very center. So the very center there, that's where the black hole is, and here's the jets coming out. And so what we find is that these powerful radio sources that were first seen by Grote-Reber, and then many astronomers since then, are powered by jets, which themselves are powered by spinning black holes in the galactic nucleus. Now, it's a spinning black hole. There's gas around it too, and I'll say a little bit more about that down the road. But it looks more and more on the basis of observational evidence that it's really the spinning black hole that's doing this. Okay. So here's the last one of the four. This is 3C273. I said this was the first quasar with the jet seen here. Let's look at it now. This is actually an image taken with Hubble, and what it shows is that, contrary to what people feared, this is actually just a regular galaxy. It's a normal, sort of heavy galaxy, but it has a hyperactive nucleus, and that hyperactive galaxy is, it's 100 or a few hundred times the luminosity of the galaxy. It's just not surprising it outshines it. It's very hard to see the galaxy around it, but it's there. That's what the optical astronomers found. And there's the spectrum of it. That's actually Schmidt's first spectrum. Here's the jet seen with a modern radio telescope. Here's something that my colleague Tony Reedhead, an earlier Jansky lecturer, found and his colleagues found in the 1970s, was if you look at the structure in here, it goes this distance, this structure here goes that distance, goes to there, to there. And if you I lost the linear scale here, it was in light years, but basically what you see on the sky is features moving at about 10 times the speed of light. You might say, well, that's contrary to what Albert Einstein told us, nothing can go faster than the speed of light, except possibly a rumor, but that's okay because it carries no information. But it appears to go faster than the speed of light. But as we now teach in freshman physics, this is just an illusion. It's just an illusion. There's nothing physically going faster than the speed of light, and that's what Einstein cared about. So it's just an illusion, but what it does say is these jets have stuff moving at very close to the speed of light, and they're pointed towards us when they do this trick. Okay? So that's something we've learned from 3C273 and many other sources. And then something I'll emphasize that it's not going to make a big deal out of it here, but we actually know a lot from this source, is that these jets are typically seen throughout the electromagnetic spectrum, and in particular at the highest energy end of the spectrum, in the gamma rays, where they're sort of particles we're looking at. The very highest energy gamma rays, we see these jets too. And this one shows that they're wildly variable. some of these quasars are variable on timescales of minutes. The flux that you see varies on timescales of minutes, so that means that the emission is coming from somewhere very, very small, as small as a black hole. Black holes, the sizes of these black holes, just to be clear, these black holes, the sizes of the black holes are about the size of the solar system. It's that small, right in the middle of a giant galaxy. And that's where all this power is coming from. Okay, so the jets can be powerful, as in this case, and they can be variable gamma ray sources. So we learned a lot by looking throughout the whole electromagnetic spectrum, not just the radio telescopes. So I'm going to show you quickly now some other sources. Here are here's a source called NGC 6251, and what you can see is jets here that you can deconstruct, and they make smaller and smaller structure. So it's just like looking at a Russian doll, if you like, where you take the pieces off and you look on smaller and smaller scales. You still see these jets. Here's another example. This is a very nearby galaxy. That's a degree. The moon and the sun are half a degree across. You can see how big it is on the sky. And right in here is a jet, and a jet going in the opposite directions, called Centaurus A. Here's another one, an X-ray jet, dead straight. Black holes in there. There's the end up there. This jet, stuff moving out at the speed of light. X-rays, dead straight. Real miracle, it does that. Here's another one. The source is almost certainly orbiting around. Here's another one. Source may be swishing around like a top, might be precessing around. Here's another one, that's the same sort of thing, called as the cosmic butterfly. Here's another one, that's two jets in orbit about each other. So there's lots and lots of areas. Every one of these has a mother who loves it. So it's really remarkable, the variety of seasons. We're learning about the jet phenomenon from all of these wonderful observations. So let's say a little bit about jet power, how this might happen. Here's one of my heroes, Michael Faraday. And in the early 19th century, he showed that if you moved an electrical conductor in a magnetic field, you made a voltage. You made electrical power. And that's the basis of many forms of generating power today. You can do the same thing with a black hole. Here we've got a spinning black hole, magnetic field lines threading it, and it spins. And so it's moving in a magnetic field. The black hole itself behaves like a pretty good conductor, not a perfect one, and it makes a voltage. So that voltage would be 1 billion trillion volts. That's an awful lot of Energizer bunnies. And if you remember Ohm's law, you can say, well, it turns out the resistance is round about 100 ohms, and so that means we're looking at 10 billion amps here. That's an awful lot of electrical current. So it's not surprising radio astronomers can see this. Okay, here's a simulation of making these jets from gas flowing around forming a disk around the black hole. And these bold lines here with the arrows on them are magnetic field lines. And so what we're saying is that we've got gas, it traps magnetic field. That magnetic field then is able to take the spin energy out of the black hole and power the jets. That's the story, and we'll come on to where this might be going. So what is the future look like? Well, this is something that I put in here, and I wasn't quite sure what I could say about it, but I read the New York Times today, and this was actually announced in the New York Times, so I'm now allowed to talk about it. This is an infrared interferometer in the European Southern Observatory in Chile. It's got an instrument there called Gravity, and basically, you can read the article in the New York Times, but basically what it has is magnetized clouds that appear to be, they can see there, orbiting very close to the black hole at infrared wavelengths, and they have periods of about 45 minutes or so. So they are seeing these orbiting clouds. We're not entirely sure what they're looking at, but it's a remarkable discovery. It's an undeniable physics that's going on very close to the black hole. Looking further into the future, there's the Event Horizon Telescope, which I mentioned, and that Event Horizon Telescope has the capacity to, in the very largest black holes that we can look at, to look down to scales of a few times the size of the black hole. Now, what they're going to see, I don't know, so I'll defer to my colleague and co-author Kip Thorne, who was the inspiration of the movie Interstellar. Did many of you see the movie Interstellar? Okay, so they saw that, and so I'm absolutely confident they're going to see it, the radio astronomers are going to see an image just like that. Right? Okay, maybe. But there's lots of simulations out there, and we'll see. I mean, it's already clear that we're on just like we have always been, we're on a trail of discovery. We don't really know what we're going to see, and it's going to be wonderful to find out, and it won't take long. So the event horizon, the first set of data is already in, and it's being analyzed right now. So on the timescale of months, or maybe by next year or so on, there'll be results from these observations. So I'd like to change gears and go from what I spent quite a bit of time talking about, which are the radio galaxies and the black holes that are responsible for them. And I'd now like to go on to talk about cosmology, where radio astronomy has also had a fantastic impact. Here's so that I can just think of going on there. Something wrong here. Oh, there we. So I think we may have. Okay, so what I showed you on the first slide. Sorry, there seems to be some problem with the advancing. What I showed you on the first slide. Let me just sort of say. Actually, I'm going to go forward here. So that's right. I know what I need to do now. Okay, thanks. So what I'm going to do is tell you a little bit about one of the reasons for building these radio telescopes in the first place. Was to try and understand the large-scale structure of the universe, called cosmology, subject called cosmology. And one of the ways of doing this was just looking at these radio sources and counting them, and seeing how many there were that were bright and how many of them were faint. And if there were many more that were faint than were bright, then that's what you would expect, because there's more volume out there when they're further away and therefore not as bright. And so the way in which you got more radio sources as you got less bright was essentially a classic way of figuring out what sort of universe we inhabited. And at that time, there were two candidate theories, I suppose, that were out there generically. One was the universe had a revolutionary beginning called the Big Bang. And the other was it's been the same, always been the same. It's just called a steady state cosmology. And after a somewhat fitful history, which I won't go into, the sources were shown to be consistent with a Big Bang cosmology and not a steady state cosmology. So this was the very first event, and there were not very many sources that were seen in the 1950s and 1960s. There were a really very small number. Nowadays, and I just got this from Jim Condon, who's here in the audience, this is this telescope Meerkat. He's just looked at a patch of the sky and gone as deep as you can. This is an extraordinary image you're seeing here, and looking it on the screen is not doing it full justice. What you've got here is about as faint as you can go, about 2 billion sources on the sky. Just to give you some measure, there's about 100 billion galaxies out there. You can see a little bit more in terms of structure, but if you count the galaxies on the whole sky, there's about 100 billion of them. So this is a few percent of the galaxies, but you're seeing very, very faint structure in very faint radio sources compared with the galaxies. So the sort of structure you're seeing here, and the very faintest sources here, is about 100 billionth of the luminosity of a typical galaxy like ours. So you're seeing radio power that is 100 billionth of the luminosity of a typical galaxy like ours. And we're seeing, 2% of all galaxies at that level. The brighter ones, or most of the brighter ones, are black holes and the jets that we've seen, but in the fainter ones you're seeing sources associated with stars. Now, this is sort of truly remarkable accomplishment, but it just illustrates what is not always appreciated, is just how sensitive radio telescopes, but also by extension radio astronomers are. They're a deeply sensitive people, so speak quietly in their presence. If you get a gamma ray astronomer, you have to hit them about the head with a 2x4. They still don't pay any attention. But the smallest nuance in a radio astronomer is sending a paper off to Nature. They really are deeply sensitive people. So, so here you see these sources counted on the sky, and of course it's all consistent now with what we know to be a Big Bang cosmology. Let's talk about the microwave background. There's somewhere in here has got lost an image. Sorry, what you did flash by of Penzias and Wilson, who in 1964 first discovered the cosmic microwave background, also sponsored by Bell Labs. And what we have here is an image now made with the Planck satellite, the orbiting Planck satellite, which looks at the microwave background. And this image, it takes a little bit of getting used to it, but you want to think of it as the whole sky. Now, it's kind of hard to put the whole sky as sort of looking at a sphere from the inside, looking at that and putting that on a piece of paper. So what you do is you essentially cut halfway across it and then stretch it out and squash it down on a piece of paper to make it something that looks a bit like an ellipse. So this is the whole sky, and that point there is equivalent to that point there, and that point there is equivalent to that point there. So we're looking at the whole sky. You might say, well, this cosmic microwave background is pretty variable stuff. The red is bright and the blue is faint, and this image here contains structure on all of these scales. But what you have to understand is that this microwave background radiation is astonishingly smooth. It's the same in all directions, except for little tiny fluctuations, and those fluctuations are 10 parts per million. So on the scale of 10 parts per million, there are fluctuations on the sky, and these are the fluctuations you're looking at. And by analyzing those fluctuations, it's an extraordinary piece of physics and especially of observational astronomy, building up the sensitivity to be able to make these measurements. You can infer that the universe has about 5% matter, about 26% so-called dark matter, which we don't know what it is, but it's there, and we know its properties, but we don't know what it is. And then 69% of so-called dark energy, which is sometimes called a cosmological constant, that causes the universe day to accelerate. And I would say the detective story that has been followed to reach these conclusions, at least half of it has essentially come from microwave background observations like this, and this is radio astronomy. There's almost certainly all of this, not almost certainly, but there's a very strong theory which has survived all sorts of challenges called inflation, that this was all set down at impossibly early times, but the age today is about 13.8 billion years. And this is a huge development from where we were, say, 30 years ago in our understanding of cosmology. Most people just do not argue with this at all. It's not a matter of debate anymore. So this is the background. This is what we now call the standard model of cosmology, starting with a hot Big Bang. So this is radio astronomy at work. So something I've been interested in is another way of measuring the universe, and this is gravitational lenses. And so these are objects where light is deflected by intervening galaxies and other structures, and that light can give you a magnified image of a background source. And what we can actually use this for is, in this instance, we can use this ALMA 8mm telescopes on the telescope in Chile. We can use it to image a background source. So we've got a regular galaxy here, and we've got a source of light there, and you're looking at it. A source of radio waves, I should say, millimeter waves, and we're looking at it. And so what we see then is, if it's just the alignment is good, as it will occasionally be, we see these rings made. And that's caused by the gravitational deflection of light. Now, this is a wonderful probe of what's going on, and that probe will give you information about all the mass that's in this here. And one of the really big questions today in cosmology is this dark matter clumped on very small scales or not? Simple theory says it should be. Most observational evidence says it may not be. And so it's a really big question now. And what this has the capacity to do is to look for this sort of small-scale structure. And here's an example of one lens that has shown the existence of this small-scale structure. It's not imaged in any way, but it's seen, it's dark, and it's inferred to be there. So we can see, using techniques like this, how much small-scale structure there is there. So, and it turns out that ALMA is an ideal instrument for gravitational lens observations. So this is one of the things that I've been involved in this collaboration, and it's been very exciting to see all this unfold. If I look to the future, and something that I've also been thinking a bit about, and this is a put that there, that's right, put that up there. This is going back to that microwave background map. Remember I showed you that fine structure on the microwave background map? Now what I want you to imagine doing is taking out all the fine-scale structure, smoothing out all of the fine-scale structure, and just looking at the largest, grossest scale structure. And so what we have here is this same sphere around us, looking back essentially to the beginning of time. We look at that structure on the sky, and then we're looking inside this sphere, and what we're trying to do is just on the very coarsest scale, put together the interior structure between the whole sphere of the universe as far as we can see. Okay? We're trying to make a three-dimensional map of the universe as far as we can see. And that's, I think, now becoming possible. We obviously make maps of little bits of the universe around us, for example. That we can do. But this is looking at the universe at large. And so the radio astronomy part of this is very much to remove the effects of our galaxy, which are a major problem in doing this, and radio astronomers are contributing to doing that. And if we then use these observations, we can then infer what the three-dimensional map looks like, and our current best effort, it's not our final effort, but our current best efforts, essentially looks like that. So on the very largest scale. So we can actually not do physics experiments here, we're doing geography. We're saying what's the structure of the actual miserable universe, wonderful universe we inhabit right now. Okay? And so I think this will get more and more interesting as we go forward in the context of cosmology. Let me now turn to the SETI harvest. Here, Frank Drake and others began Project OSMA at Green Bank using the Tatel telescope, and they were doing the search for extraterrestrial signals. As is well known, they were found, but it's all been suppressed by the government. So let's move on. So here we are. Sorry, I meant to show that one. And then there are various stratagems, and we just hope that extraterrestrials are as smart as our radio astronomers in knowing where to transmit their signals so we can see them. So there have been various stratagems for trying to find them. And this is now, again, being, I think it's something that's well worth doing. A lot of it can be done passively. The Green Bank telescope is being used for this, courtesy of the Yuri Milner and the Breakthrough Listen project. And as I say, nothing has been found yet, but searches are being done for, I Love Lucy reruns or their functional equivalent, transmitted out into space by nearby stars. And this is, I think, a very exciting way forward. I'd like to FAST, the giant Chinese telescope, is also getting in the act here and is ideal for these purposes. I'd like to take this in watch the space, as they say, yes. But I'd like to take this in a slightly different direction as to what has been probably one of the most publicized images from NRAO and from ALMA, because it really was a stunner when we first saw it, was this new, very young million-year-old star called HL Tau, and it, something seems to have gone wrong with my last set of edits seem to have gone funny. Okay, let's do this here. So anyway, so what we've got here is HL Tau, and this is a star, a very young star, and very young stars have rings and disks of gas and rocks around them. And this was seen by ALMA telescope to be broken up into these gaps here, which were presumably made by protoplanets and so on. I haven't got time to go through the theory of this. We now know, of course, from optical observations that there are exoplanets everywhere. Here's the famous TRAPPIST-1 system. This one, HL Tau, also actually has two jets associated with it. And so there's jets, I can't see the other one here, but there's a jet associated with it. So this is just like the black hole. It has a disk around it, presumably has magnetic field. And those, without a black hole, you can still make jets. And these jets here are associated with this HL Tau system. And here's, say, it's a famous multi-planet system called TRAPPIST-1 after a Belgian beer. Don't ask. Okay. So protostellar disks, they also make jets and probably magnetically. And this has been one of the many advances that ALMA and by extension NRAO has fostered in this area. Another is, of course, is looking at all the interstellar molecules, which are a tremendous source of intelligence for interstellar chemistry and so on, for learning about whether the molecules that one needs for biology are actually being made. So let me go on. Okay. So what about the future of this business? And here I'm going to go out on a limb, and this is going to be my speculation. One of the other things we've learned from radio astronomy is that many of these stars and so on are actually rather hostile to life as we know it. There's a lot of solar activity, there's a lot of cosmic rays, a lot of X-rays and so on. You wouldn't want to live there. You wouldn't be buying real estate there. Okay? So I would have a speculation that that in fact life in these places it may well be subterranean. It may well be in a shielded environment beneath the surface of rocks and beneath the surface of planets. And the other thing we've learned from having all of these exoplanetary systems that are so crowded, they keep on throwing out debris into interstellar space. All the time, the interstellar space will be lousy with these rocks and planets and so on. Sometimes we call them rogue planets or free-floating planets. I like to call them nomads because they may carry their flocks with them. They may actually carry, in a minority of cases, microbial life or something like that. And there could be a vast ecosystem out there or not. And this now, I think, becomes a scientific proposition to test. And I have a completely open mind as to what the answer is, but I think now it's going to be one. And radio astronomy is going to be a large part of this. So, and they may harbour, as I say, subsurface ecosystems. So there may be a vast sort of ecology out there or not. And I think this is again where this field is going. And for reasons I can't get into here, radio astronomy have a lot to say. Finally, I'll talk about the pulsar harvest. I'm getting near the end of my time. I think can't read too well. Yeah, there we are. So quickly about the pulsar harvest, and here I was actually first year undergraduate in Cambridge when this happened. This was the discovery, for sure, of spinning magnetized neutron stars by Jocelyn Bell and Tony Hewish. This is them at that time, looking rather happy because they'd just seen this tick, tick, tick. And what they were actually looking at from a regular ticking source, they called them little green men first of all, but that didn't last very long. They were spinning magnetized neutron stars. And they're called pulsars. They called them pulsars because they went pulse, pulse, pulse. And so they're pulsars and they're spinning magnetized neutron stars. And these are objects that are they're stars. They've got the mass of a sun, say, but they're about 12 miles in diameter. So they're really very compressed, and therefore they can spin very rapidly. And here's a sort of anatomy of a neutron star, if you like. And the periods, a day on a neutron star can range from 1.4 milliseconds to 24 seconds. Okay, that's the range that we have there. 1.4 milliseconds, a thousandth of a second. We can have those. Here's one of the famous ones. It's in the middle of the Crab Nebula, seen in optical and in X-rays. It illuminates the whole thing. Okay, it illuminates the whole thing. So the spinning magnetized neutron star is just like a black hole, is an amazing power source. And these pulsars have turned out to be extraordinary laboratories for doing physics of many, many different. In fact, I once gave a talk where essentially I challenged the audience to find a type of validated physics that was not being applied to neutron stars, and I won. So the string theory is not so obviously applicable, but it's not yet validated physics. But the other thing is they're even more important as tools. Just by having this clock moving in on the other side of the universe or moving in and out of a gravitational potential well, just having that clock there is remarkable. And it's a very valuable tool for learning about physics and what lies in between. So here are pulsars. So we have, as I say, if we think, as I mentioned before, about regular gravity according to Isaac Newton, and then general relativity according to Albert Einstein, they pretty much agree on almost everything that you'll do, throwing apples around or stuff like that. They'll agree with all of that. But then with these very fine, careful measurements, you can distinguish the two. And so far, every time we've looked, and in particular if we look at two neutron stars orbiting each other, as we found about 10 examples of these things, of two neutron stars orbiting each other, then by looking at the general relativity description of this relative to the Newtonian theory, we find that general relativity agrees superbly well and its differences from Newtonian theories. This is one of the main reasons why we believe general relativity. And what you're seeing here is something that, of course, is being made very famous lately, but it's the first example of this, and that is that two neutron stars in orbit about each other like that, they will radiate gravitational waves. And that loss of energy by the gravitational waves corresponds to a shrinking of the orbit. And so these are called binary pulsars, and the answer agrees with Einstein. And in the particular case, the one that was first discovered in 1974, in which I was privileged to work on some of the analysis of it, and that we know will merge in 310 million years. Now, we're kind of impatient, so people have been looking for these things generally, but they were able to measure the shrinkage of the orbit. And that agreed with general relativity, like the other tests, to better than 1 part in 1,000. This is not a touchy-feely thing. This is an accurate measurement that shows that general relativity is good to 1 part in 1,000. In some cases, better than that. Okay, so where's the future going? Okay, I'm going to, in the interest of time, leave out the fast radio burst, which I talked about yesterday, and just go forward to here. This is something that was obviously in the newspapers a lot last year, and in fact previous years, was the experiment to the telescopes to directly measure gravitational radiation. This is called LIGO, and there's a European version called Virgo. And together they measured gravitational waves directly. They saw the waves going past a detector. And the most recent source was one on the 17th of August last year, and it was two neutron stars, just like I said, but not waiting the 230 million years. This was another pair of neutron stars that were coalescing together. And in the final second, they saw these gravitational waves, and again, everything just fits perfectly with the theory. And this is truly a remarkable thing to have happened, because it has opened up a Pandora's box of physics. And that Pandora's box contains, I like to think of it as a glass half full, with validated conjectures. We've learned that gravitational wave travels at the speed of light and so on. We've learned that general relativity appears to be almost exactly correct. We've learned its relationship to sources called gamma ray bursts. All the things that we could have hoped to corroborate seem to be checking out well. And then it's a glass half empty because there's discovery space there. It's telling us about nuclear physics. It's telling us about where the elements come from, all of the heavy elements. If you think about, many of the heavy elements, it's telling those, if you like jewelry, the platinum, the gold, and the silver, they come from the coalescence of neutron stars, we believe, in these systems. If you wear cheap zirconium, that comes from elsewhere. So the good stuff comes from these coalescing neutron stars. And then radio astronomers, they look like they've been left out of the party, and then they've just got back in the act, and they've shown that these sources make jets, and they can see the jets move across the sky. So radio astronomy has an enormous role to play in the future of this field, which will restart in February when the LIGO systems get fired up again, and they'll be looking with the increased sensitivity for more gravitational wave sources. So I like to think of this as quasars for the impatient. In quasars, you have to wait a long time for something to happen. Here in the neutron stars, we see the system. So, I was going to go back here. Yeah, so I'd just like to finish at this point and say I'm really pleased to be here. I hope I've been able to give just a little bit of a flavor of where radio astronomy started from my perspective. It's a sort of more homage than a history. And to tell you about the sort of 5 harvests, the telescopes, the radio sources, the SETI and the neutron stars, and I'd like to say that, you know, my own involvement of this has been a little, in some sense, peripheral, but I'm sort of proud of the things I've been involved with, associating trying to understand some of these things. And insofar as I'm here receiving a Jansky, which I'm deeply grateful and honored, I really want to share that credit with my many collaborators over the years, and I actually make a montage of them. So to them, to Carl Jansky for starting all of this, and to NRAO and its wonderful director and its directors of yore, I thank you very much indeed.
Thank you, Roger. Questions? Yeah.
So no, I'm just trying to hear.
So when the jets of energy from the black holes that you talked about earlier in the presentation, what exactly happens to say stars or even like another galaxy that happens to be in the way of it?
Oh, okay.
Would you repeat the question? So
Yes.
the question is, what happens to other stars and galaxies that are in the way of the jets emitted by the centers of galaxies?
Okay, people have thought of that, and in fact, I was talking to somebody at NRAO this afternoon about this. There are a few examples where you may get a direct hit, and it's a little bit more likely than you might think because these jets can move around a bit, so you get more of a chance of hitting something. What is thought to happen, is likely to happen, is if that galaxy contains a lot of gas, you're quite likely to stimulate star formation, the formation of fresh stars. So you should see lots of young blue stars in that galaxy if it's in the way. So yeah, that's something that ought to happen. It can happen on a smaller scale, not with whole galaxies, but clouds of molecular gas, which are the sort of nurseries of regular stars. If they get in the way, they can also, obviously it can be pushed, but it can also make stars.
Kevin?
Does it make you uncomfortable that mathematics and physics does such a good job of explaining the universe, or seemingly explaining the universe?
Well, hang on. So,
yes, go ahead.
A difficult question. Does it make you uncomfortable that mathematics and physics does such a good job in explaining the universe?
I think, to be honest, doesn't make me uncomfortable. It certainly surprises me. I mean, I think many people have waxed lyrical on this point, that one of the most remarkable things about the universe is that it is so much of it is explicable in this way, and the model, for example, of cosmology that has emerged out of so many otherwise credible possibilities is really quite simple. It's not the very simplest it could be, but it's the next most simple. And it could have been so messy and so meteorological and so on, and yet it's something very simple. General relativity is embodied in an equation, G equals 8 pi t, we'll say. So it's something very simple. Now, at the time when we didn't know if it was right, there were a whole plethora of much more complicated things with this Baroque ornamentation of theory there. And we don't need it. The simple things work. Now, am I disturbed by it? No, but I am a little surprised. Yeah, I'll share the surprise, but I'll take that.
Time for one more question. Yes.
You mentioned that our observations, particularly around the spinning pulsars, deviates, not very much
from general relativity, is the difference an error in measurement, or is there actually a deviation from general relativity from our observation?
No, sorry, I may not have been clear there. Everything we have measured in these neutron star systems, in fact there are the best studied cases, is consistent with general relativity. Can we do much better? The answer is probably no, because there are extra effects, in particular the motion of the neutron system in our galaxy, which are very hard to guess what those corrections should be. So in some sense we're going to be measuring those corrections. But as yet there's no credible measurement that is inconsistent with the general theory of relativity. And some of them are good down to about 50 parts per million.
Okay, well on behalf of AUI and NRAO, I'd like to thank all of you for attending tonight, and let's thank Roger again.
Thank you very much.